Accept that. So if we could go through and underline all the useful information. So what's the useful information? Okay, so I like how you started out strong with that 745 milliliters of acid. Is the acid important? Yes, it is absolutely critical to solving this. It is the substance of that measurement. Yes, it is super important. Yes, you should say it. Okay, what else is in there?
She adds 0.2 moles over liters of barium hydroxide.
Okay, so it's a bit hard to do in this tiny little space there, but what we might do is pull that information out so we could write it out. So I liked that adjustment, recognizing that that capital M meant moles per liter. And this was our barium hydroxide. Any issues with what I wrote?
So, liters of solution.
That's liters of solution, not 2. Be 1 liter of solution.
Hydroxide is a charge of
The fish state would need to be written in BaOH2. Okay, what else do we have?
Milliliters of barium hydroxide.
Okay. Any other given information?
moles of hydroxide are equal to the moles of hydrogen.
Okay, and that one becomes a bit tricky to deal with. We'll look at that one in a second. Anything else useful?
So what is the molarity of the
What's the actual question, right? We just underlined all this useful information, but we haven't identified what the question is. Good. The question is, what is the molarity of nitric acid? Which should help us out, because there we see the reference to acid again. So the acid over there is probably referencing the nitric acid, yeah? Okay. Anything else? And you can say no, that's fine. No. Okay, so let's set it up. What are we solving for? So I heard a couple different responses there, but that might have been just the shuffling of language. Molarity of nitric acid. So I heard a couple people starting to say moles or working through moles, but what they might have been saying is that molarity is a dumb thing to solve for. What we need to be solving for is its actual full unit, which is moles of the nitric acid over liters of solution. Yeah? Good? Okay. Now what? As far as given information goes, we've got at least 3 things given, sometimes arguably maybe 4. So which of those 3 or 4 things do you want to start with? This is actually just one equation. We can do it in one whole big fell swoop. Milliliters of the acid. Right? Cool. That's a good place to start. Where should I place milliliters of the acid? Numerator or denominator? Oh, we got an interesting answer here. We got numerator and denominator. Only one can be correct. Milliliters is a measure of volume. Liters is a measure of volume. Where does your volume measurement show up in your answer? In the denominator. Where should your volume measurement from the given information show up then? So I do find this interesting because when we go through and do this, I keep hearing it. Okay? We have an answer show up in the numerator. So where do we place the given information? Oh, let's place it in the denominator. Okay? Or something shows up in the denominator in our answer, so you want to place it in the numerator. So let's try this a little bit less generically. I want to solve for 1 over 2. Where should I place the 2 on the left-hand side? Okay? 2 over 1 equals 1 over 2.
No, I thought we were canceling.
Okay? That might be the issue. I thought we're canceling. At no point have we talked about cross multiplication, because the cross multiplication process doesn't work well. They allow you to do individual short steps. It does not allow you to solve an entire question. The only reason that cross multiply method works is if you have an equation. There are 5 steps, I think, to this, which means you would need 5 equations. How many of you know one of those equations? Okay, so cross multiply, bad. I want the right to look like the left, which means if volume of solution shows up in the denominator, where does it need to show up on the solve part of my equation? In the denominator. Okay? And I already went through and starred our 745 milliliters of acid. Okay? And I think that's because you guys suggested that. Was there another volume you could have used? 165 milliliters of barium hydroxide. Well, there's 2 volumes. Which one should go in the denominator? Okay. To answer that question, we need to be a bit more specific with our units over here. This is moles of nitric acid in liters of what solution? It is not both mixed. This would be the molarity of the nitric acid solution before you did anything to it, which means this is liters of nitric acid solution. If you use that 165 milliliters of barium hydroxide, that's the wrong one. That's not referencing the nitric acid solution, that's referencing the barium hydroxide solution. So we have to be careful with our choice of these volumes. So when we talked about substances being critical to solve a question, if we ignore the substance, we have 2 volumes, 745 milliliters or 165 milliliters. Depending on which one you use, your answer is entirely wrong. So it makes a really big deal to narrow down what substance you're looking at. If you aren't looking at the right substance, everything is wrong. This is why you need the entire unit. So which one do I want to use?
Nitric acid.
The nitric acid one. Which is that? What?
That one up there.
The red one. I'll accept that. Where did I want to place that unit?
On the bottom.
I wanted to place that in the denominator because my volume measurement at the end needs to show up where? In the denominator. What should show up in the numerator? It's a tricky one. When we start with something in the denominator, it makes it very difficult to figure out what should go in the numerator. It's 1. Okay. The given piece of information was the volume of the acid. It wasn't given with respect to anything else. By placing it in the denominator, what am I saying? I just need to divide. It's telling me what is the mathematical operation I want to do with that given piece of information. The mathematical operation is to divide. Okay, so that's a decent place to start. Is milliliters of solution what we want?
No, I want these.
So what do you got to do?
There's
I want milliliters in the numerator so that what?
so you can get liters.
So that can cancel. What do I want to relate that milliliters to? Liters of solution. Awesome. Where do I find that conversion factor? This is something that you have to memorize. Okay? Where 1 milliliter was 10 to the minus 3 liters of solution.
You don't want us to do like 1,000 over 1?
I do not reference my previous discussions about that. Okay? And it's not wrong. It's just, well, that's all I would really say is reference those other discussions. Okay? So that gets us liters of solution in the denominator. That's fantastic. But we don't have moles of nitric acid. We should get some moles. Where do we get those moles? Through a conversion. Conversion of what? Liters to moles. There's a suggestion liters to moles, and I'm going to run that you're suggesting this liters should become moles here. That's going to become problematic because that liters of solution is that liters of solution. So if you converted those liters into moles, what happened? You would have lost your liters of solution, and you've actually undone work you've been trying to do. Where do I get the moles of nitric acid? Periodic table. So let's go up to the periodic table. Okay, and let's try and get some moles off the periodic table. When we go to the periodic table, what could we find? So what are you suggesting we do off the periodic table? A mass of H, which is 1, nitrogen 14, oxygen is 16 times 3, 48.
Yeah.
58, 62, 63. Did I do that right? You have calculators. Like, that's what you were supposed to bring to class. I'm not a math person. I can manipulate stuff. That's about it. You get 53? Damn it. 63. Good enough. 0.09? Not sure how much well, maybe I believe that. No, I don't think I believe that. We're just going to run with it, though. What are the units on that? Grams of nitric acid per mole of nitric acid. How many moles of nitric acid? 1 mole of nitric acid. Cool. So could I use that? I could. How could I use it? I want the moles in the numerator. Awesome. I want the grams in the denominator. 63.091. Yeah? And now I would need to cancel the grams. With what? Does the question give you anything about grams of nitric acid? No. Okay. So this is an interesting observation. So I just want to say, step one, I'm proud of a lot of you here because a lot of you are writing stuff down. It's unfortunately wrong. Okay. What you need to be asking is, why are we doing these steps? Not just writing stuff down. Does converting moles to grams get us closer to an answer? Yes, we bring in moles, but we also bring in the units of grams of nitric acid. Am I given grams of nitric acid? No. At no point am I actually even given a mass. Not even up there. Does this conversion factor exist? Yes. Could I use it? Yes. Is it useful? No. This is ineffective. Okay? You're like, damn, I know. This is when you should be struggling, trying to figure out, when should I use something? Why should I use it? Okay? I would have to see grams of nitric acid in the question. Minimally, ideally, I would have to see some mass in the question, because then maybe I could do a conversion, right? There's no mass given. So while going to the periodic table does bring in moles of nitric acid, can moles show up in another way? Yes. We could do moles to molecules. Okay. Thank you, Mr. Avocado's number. 6.022 times 10 to the 23rd. What's our thing in this case? Molecules of nitric acid equals 1 mole of nitric acid. Cool, we've got moles of nitric acid again. That's exactly what I wanted. Moles, HNO3, molecules, HNO3, 1 mole, 6.022 times 10 to the 23rd. For those of you who can't read what I wrote, hold your breath. I take too long to explain things. Don't hold your breath. Am I given molecules of nitric acid? No. Am I given the unit of molecules in the question? So while this also brings in moles, not a useful conversion. Where else can I find moles?
Isn't the liters, like convert liters to moles with the 22.4 liters equals 1 mole?
So, you've done the reading. Cool. Unfortunately, I'm behind in the lecture, so I couldn't have railed on you for the 22.4 liters equals 1 mole. There's this equation that we will see very shortly. 22.4 liters equals 1 mole, which is a phenomenal equality. It works when? Gases. Are we a gas? No. So, no, it's invalid.
So it says you got 745 milliliters of acid, nitric acid,
Yeah, we used it.
and then you're adding in your 650 milliliters of barium hydroxide to equal that. So it says at this point the moles of hydroxide equal, and it's at 0.2 moles over liters.
So what you're saying is that we should look at the rest of the given information and say, what the hell are they? Why was that there? That's an interesting idea. It's saying, let's take advantage of that other information. That other information is about what species, though? Barium hydroxide, not nitric acid. What would that barium hydroxide do with the nitric acid? I don't know. What would happen if we say, took barium hydroxide, and actually let's rephrase that. Let's say that we took nitric acid, because that's what we started with, right? So HNO3, and then it was mixed with barium hydroxide. Well, what would happen? That looks kind of like a chemical equation. And because of Unit 2, and I studied all the chemical reactions, and I know what chemical reactions look like, I know that that chemical reaction is, I'll accept 2 answers. One is more correct. What do you got?
Double replacement.
Double replacement. There's a better, more correct one. Neutralization. And because I know that reaction type, I know what the products are going to be of that reaction. I know those products are going to be CO2 and H2O would be a fantastic product for combustion reactions. We said double replacement neutralization, so no. Barium nitrate and water. I'm going to argue that writing it as HOH is actually more sensical, is more effective to be able to see how to balance this question. We're taking the H from nitrate, and I'm combining it with the OH from barium hydroxide to make H and OH, right? We can see those pieces better. Right? The balanced chemical equation gives me what? Half right. The mole ratio. Okay, so that if I know the moles of barium hydroxide, I know how many moles of barium nitrate could be produced. If I know the moles of barium hydroxide, I know how many moles of water could be produced. But probably most importantly, if I know the moles of barium hydroxide, I know how many moles of nitric acid are necessary to react. The balanced chemical equation gives me that. Was there a tip-off that I should have been looking at a balanced chemical equation?
At this point, moles of hydroxide equal.
Okay? We've got an expression, moles of hydroxide equals something else. We're showing a relationship between what? Hydroxide and hydrogen ion. We're showing the relationship between what? And don't tell me hydroxide and hydrogen ion. I know, it's a weird, vague question. Substances. It's a substance conversion. Okay? I don't know anything about the moles of nitric acid. I'm going to have to figure them out from somewhere. What else was I given information about? Barium hydroxide. If I'm going to use the information of barium hydroxide, what am I going to need to do?
Figure out how many moles you use.
I need to be able to do a substance conversion, which comes from a balanced chemical equation. Okay? So what is that mole-mole ratio of barium hydroxide to nitric acid? 745 is milliliters, not moles, so that doesn't work. I really hope this doesn't come back and bite me, but we'll see. Where's the information related moles of one substance to the moles of the other? It's from the balanced chemical equation, which means I should be looking at the chemical equation. If I'm not looking at the chemical equation to find those numbers, I'm wrong. Right? And where in particular in that chemical equation should I be looking? The coefficients. So what is that mole ratio? Okay, before we do that, we want moles of nitric acid, and we're relating them from moles of barium hydroxide. So what is that ratio? 1 to 1. This is Mike intentionally leading you down a nasty path that multiple people, even the person that suggested 1 to 1, has called out. What's the issue with calling it 1 to 1? It's not a balanced chemical equation. It has to be balanced. Right? Is it balanced? So what do you have to do to fix it? Balance which? Right? I would need an extra hydroxide because there's 2 here, right? And there's only 1 here, so I could put a 2 in there. Is it now balanced? Now I would need a 2 in front of the nitric acid. Is it balanced now? Why not? There's only 1 nitrate, so I would need a 2 in front of this one. But now I would need 2 bariums. And someone said it, because now I need 4 hydroxides. But now I need 4 hydrogens. Oh my God, what the hell did I forget?
Never going to have enough.
Just like life.
It's barium nitrate too.
Barium nitrate was written incorrectly. Barium's a +2, nitrate is -1, which means I need to have 2. The formulas must be balanced before you balance the equation. Wait, that wasn't one of the steps of balancing equations. Yes, it was. It's in fact the very first step. Nope. I trust you too much. Not helping you anymore. So now what can we do? Now you're like, well, fine. I'm not going to help you anymore.
It's a trap.
2 hydroxides, 2 nitric acids, barium balanced, hydroxides balanced, hydrogen balanced, nitrates are balanced. What do I use from that chemical equation, my conversion? 2 moles of nitric acid is 1 mole of barium hydroxide. This is fantastic. I brought in moles of nitric acid. I found the conversion factor that brings in moles. That's great. Okay? We literally tried all of them. Okay? Practice helps you to pick up those patterns to find out which one you should try. What should you do? You should try them all and be like, well, crap, that didn't work. That's a good thing. That is an exceptionally good thing. You have proven mistakes that you can now not make again. Do I want moles of barium hydroxide in my answer? No. So what do I got to do? I got to get rid of it. Am I given just the moles of barium hydroxide? No. So what am I going to relate the moles of barium hydroxide to? Liters of solution. Conveniently, because I saw that capital M was there and I was like, I need to write that as the proper unit, moles over liters, that thing now shows up super cleanly. What if you didn't write it as moles over liters? You're going to be left with capital M, and well, how do I get moles and liters? Yeah, that's going to become a problem. That's why you should write it out. Right? What numbers need to show up in there? Those ones, I'll accept that. Okay. Is that liters of solution that I just wrote the same as the liters of solution over here in green? No, why not? Why aren't these the same thing?
Oh, I'm sorry. I was looking at spelling. They are.
This was liters of solution of nitric acid. This is liters of solution of barium hydroxide. Substance can be tricky. Those are different liters units. They are not the same. Okay? So now what do? Have I got my answer yet? I've got moles of nitric acid per liter of my nitric acid solution. That looks pretty good, except I also have the liters of barium hydroxide, which means I need to get rid of that. Do I have the liters of that solution? No, but I have milliliters, which means I can do milliliters to liters. 10 to the minus 3, 1 milliliter. Right? Now I need to cancel the milliliter unit. And this sucks because what happened? I'm out of freaking paper. But I think I can cheat.
Just make more paper.
You gotta love technology sometimes.
I know it's stretch.
Okay? Your liters of solution cancel. I need to cancel the milliliters. So 165 milliliters of solution over 1. That cancels out. Now what do? I got to plug this into my calculator and solve it all out. Okay? Before I start punching things in the calculator, I might take a careful look at this. My second calculation in green says to do what? Divide by 10 to the negative 3. My second to last calculation, also known as penultimate, multiply by 10 to the negative 3, which means they cancel out. You will often see people not include that calculation. Just be like, oh, the units cancel. No, they don't cancel. That work should be shown there. By deleting that work, what you're doing is hiding the information, which could lead to mistakes. If you want to trust and rely on your own abilities to ensure that it is there, that is your choice. But I will always write out this work. That said, I won't make you do that.
But you don't necessarily put it into the calculator.
You definitely don't have to put it into the calculator because it cancels.
It should be there, but not inputted.
So now what do we do? What's in the numerator? 2 times 0.2 times 165. What's in the denominator? 745. Everybody see all that? What does our calculator spit out?
5.9, we rounded it.
Gah. Moles HNO3 per 1 liter of solution. I heard that it was 5.9.
Yeah.
Okay, so 0.08859 moles of nitric acid per liter of solution. Who's correct, 0.0885 or 0.08859?
0.089.
Trick question, they're both wrong. They're both wrong because
0.88.
we'd have to go back to our question to identify sig figs, and our sig fig count is 3, which means our answer needs to become 88. 6. Should not be, for those people saying it, 0.089. That first 0 is not significant. Okay? To be significant, it must have a significant digit to the left. It does not have one. So 0.0886.
Yay.
You can do that. You can do them all. Okay. Can't do that? That's cool. You got a week and a half to practice. Okay. Word questions are difficult because of the text and stuff built in behind them that you have to be able to interpret and pull that information out. This is a chemistry class. In chemistry, our goal is to do what? Make life miserable. Try something else. Different answer than try something other than chemistry. You should keep trying chemistry.
Convert something into something else.
Something into something else. So if you're starting a long word question and it doesn't look like you're converting substances, that should be a red flag that maybe something weird is going on there. Okay? So reread your question and identify. Look for substances. If it only says one substance through the entire question, then it's probably not a chemistry question. It's just a math conversion question. Chemistry is about those equations and how we convert one substance to another. Kind of make sense? Cool. You guys want a breather from conversions? Or the one person that said they didn't want a breather, tough. We're going to move into chapter 10. We're looking at gases. Okay? Bunch of properties of gases. These are things we've already discussed before, so they aren't a big deal. One thing that I'll throw in there is number 4 that's kind of new. They will mix uniformly with other gases in the same container. Okay? That's in an ideal world. Okay? Do we want to deal with gases in an ideal world, or do we want to deal with them in a real world?
Real world.
You want to deal with them in a real world. They're murderers, right?
Yep.
Yeah, so we should avoid murderers, right? But you don't know who a murderer is, do you? Which means if you're going to deal with life in the real world, you are making the assumption that everybody around you is not a murderer. That's an ideal world situation, not a real world situation, because they could be murderers.
I feel like this
Right.
went back really fast.
So what does that mean? When we look at how we model our universe and the people and things around us, what do we look to? We look to the ideal system. We don't look to real systems because real systems become much trickier to deal with. Okay? So this is the ideal system for us. Okay? One of the things that's kind of neat behind this, which ties in with this mix uniformly, okay, is that those gas particles don't interact with each other, which kind of makes sense because the space between individual gas particles is big. That's why they're gases. Okay, and they just bounce off of each other when they impact. Okay? But that bouncing is a force. Okay, so they are pushing on the sides of the container. That force we call pressure when we talk about gases. Okay? So, in our ideal gases, okay, let's take a look at some of these kind of ideal systems. Number one, super tiny molecules. What molecule isn't super tiny? Wasn't that the whole point of scaling moles and all that, was that all our molecules were super tiny? Well, yeah, then why is this such a big deal to include? They are so small for gases, they have no volume. Okay? Our particles are so small that they don't exist. And yet they still must exist because we can feel their presence on the sides of the container. We can feel that pressure. To give an idea of how kind of weird this is, if we looked at the volume of this room, length by width times height, right? Okay. And we just said, okay, first person walks in, they can sit where? Anywhere. Second person walks in, where do they sit? Anywhere but where the first person is. Which means when we start adding people to a room, what happens to the volume? It changes. That's not the case for ideal gases. For an ideal gas, every molecule that goes in can exist anywhere in that entire volume, even where there's other gas particles. And that might sound like a weird concept, but you have to think about the space in between those atoms. The space is so freaking large that by the time another atom got to that other space, that the volume loss was negligible. Okay? Random motion, straight lines. So we don't get curves, they just go straight lines. Why? You ever tried to hit a curve ball? Okay, versus just a straight ball. Like one person laughs, so I'm going to guess only one person has ever tried to hit a curve ball. Okay? It's harder to hit it when the ball moves. Okay? It's less predictable. So we assume straight lines. Okay? The next one, no attraction for one another. Okay? Two particles move by each other, zero response. Okay? The only time we get any interaction is when they hit each other, and even then, what's going to happen is they collide and they bounce away from each other. No loss in energy, so it's a perfect system. Okay? These are all fundamentally kind of flawed things in the real world, but each of these assumptions allows us to simplify the mathematics behind how gases work so that we can model their behavior better and understand them at a simple level first. Anybody want to do chemical engineering? Cool. If you did, you get to study this in a whole lot more depth where they're real gases, and then everything hits the fan. Okay? Last one, kinetic energy is proportional to the temperature. Okay? So that means you increase the temperature, you also increase kinetic energy. What is kinetic energy? How fast they're moving. So the hotter it is, the more it moves. The colder it is, less it moves. Okay? If we put all of these things together, I'm going to throw them under the bus. We get David's favorite expression. Probably wasn't favorite, but suggested expression. 1 mole equals 22.4 liters. Okay? This is unfortunately something you have to memorize. Why is it unfortunate? When is this true? When it's a gas. How many of you have worked with gases in the lab? In the lab, where you isolated, grabbed a hold of a gas, and did something with it. Not just, here's a gas, I made it disappear off. Hardly anybody. So we're having you memorize this expression for something that you don't work with. Okay, that's a bit silly, but okay, let's just say for giggles that we use it. Okay? Because maybe it's just universally true, and that's why we would make you memorize it. What's in the parentheses? When at STP. So when already suggests conditions. So this expression is true all the time as long as we're at STP. Well, what is STP? And already as soon as we hit the as long as, you're probably screaming in your head, oh, there's exceptions. There's a crap ton of exceptions, which is why this is a stupid expression to memorize. Okay? STP. Standard temperature and pressure. Standard. Okay? Like distances. The standard distance is a foot. Right? Around the world, everybody uses a foot to measure length. No. Okay, so that becomes challenging. Well, maybe temperature. Standard temperatures are consistent. Everybody uses kelvins. No, that wasn't true either. Right, so standard temperature is a challenging term because there's 3 different temperature systems that are all going to give you different numerics. Right? Okay, so that's a bit questionable. But at least standard temperature would be a temperature that would be most common. So regardless of what unit you used, it was at least a normal value, like room temperature, right? That would make sense. Something that everybody would be at when they worked in a lab. What standard temperature? Zero degrees Celsius, also known as 32 degrees Fahrenheit. Okay. For those of you in the Fahrenheit system, that might help. 32 degrees Fahrenheit. When was the last time you were at 32 degrees Fahrenheit? Okay. During the winter. So the majority of our existence in this area of the state, we will never be allowed to use that conversion factor because we're not at 32 degrees. That's a pretty dumb conversion factor. Okay. So let's move to the next one, standard pressure. At least the pressure is a little bit more sensical. Okay, standard pressure, okay, is fairly constant. Okay, it's defined as 1 atmosphere. Where is it 1 atmosphere? At sea level. Are we at sea level? No, which means we're not at standard pressure, which means this expression also false. So we want you to memorize an expression for a substance that you don't work with, okay, at a temperature that you'll never be at for long to do an experiment, okay, and at a pressure that you likely won't ever be at. This sounds like a dumb conversion factor, and that's because it is. Okay? It is used because it's neat and beautifully comes out of ideal gas systems. Okay? You will be required to use this, and it will shortcut some calculations. It will shortcut calculations that involve what? Gases. At standard temperature and standard pressure. What if it's a liquid? Can't use it. What if it's an aqueous solution? Can't use it. What do you use for aqueous solutions? Liters doesn't quite work because that's not a conversion factor. We're relating liters to moles. We use molarity. So the question we just solved, we had to use a molarity. We had to use a concentration because we don't have this expression. Does that make sense? Okay. So, let's use it. How many liters are needed to hold 2 grams of hydrogen gas? Set it up. Or here, I'll set it up for you. What are we solving for? There we go. Liters of hydrogen gas. Yes, technically you should include the of. You can get lazy and not include it. That's fine. Who cares about prepositions anyway? It is prepositions. I always ask. What were we given to start with? Grams of hydrogen gas. What's our symbol for hydrogen gas? H2. 2 grams of hydrogen gas needs to become liters of hydrogen gas. Set up your work. If you got questions. Okay, let's do your way. That's fine with me. Where did you go? What did you start with?
Started out with that, and then I did the conversion of moles to grams.
Okay, so pause. Give me a sec. So Megan's suggestion is that she wants to go grams to moles. And actually, arguably, based on the way you said it, you said grams to moles.
No. I said moles to grams.
Okay. Fair enough. Either way it
I
said,
started out with it flipped, and I flipped it back.
we should be careful with the placement of our units. We need to place those units according to what we're trying to do. You were trying to cancel grams, so the grams of H2 needs to go in the denominator so that it can cancel. Does that conversion factor exist? Where does it exist? That comes from the periodic table. The periodic table tells us for H, 1.01 grams per mole. We have H2, so we would need to double it, and it becomes 2.02 grams to 1 mole. Why did you do that conversion?
Because I wanted to be able to use the next conversion of moles to liters.
Okay. How did you know you needed to do that next conversion?
Because I wanted to finish with liters.
So what you went through and said in your solve was that I want liters of H2 moles, 22.4 liters mole. So you were like, this is what I think. And because I'm thinking that, I can't see it, but because I'm thinking that thing in purple, I need to do the thing in red.
Yeah.
Okay. What do you guys think? Am I going to object to that?
You're gonna argue with the process.
I'm going to argue a little bit with the process. Okay. What's the process I'm arguing with?
You're working backwards or
I'm fine with working backwards too.
skipping steps. I don't know.
You decided you wanted to go into moles because of the liter to mole conversion that you held in your head. Why not just write, whoops, let's get the pen out. Why not do that one first? Because arguably you did that in your head. You're holding that in your head. Why not just write it down? Okay? Because you wanted to cancel grams. You didn't like writing a conversion factor without things canceling. That's a personal preference. That's fine. Okay? The problem that I'm going to have with that initial process is that you had to hold that information in your head, and you had to hold it in your head while looking at other conversion factors with other numbers, which means by the time you get to the conversion factor that you wanted to use, what may very well happen? You'll forget it. Okay? And it really isn't a huge issue. All I'm trying to do is point out the process behind why you're making the actions you are. Okay? If you are comfortable with your process, okay, right or wrong, that's really your choice. I'm going to be a little upset if you're wrong. Okay? But that's fine. So the other way to solve would have been to say, well, I want liters, so I'm going to deal with getting liters in first. Oh, crap, I can't cancel any units. But what's the beauty of doing that? I now know very specifically that I need the grams and moles to cancel out. Okay? That now very clearly shows the piece. I know that that piece has to be found somewhere. Whereas if you're holding it in your head, well, what conversion do I need to do? You're now trying to hold on to one fact while at the same time thinking about another fact. Okay? That could lead to loss.
And then once I got to that step, then I had to go back and I had to flip it because I did have it wrong first.
Okay? Make sense? Okay. Are either of those correct based off of the question? When is that conversion factor true? For a gas at Standard temperature and pressure. Does the question say anything about temperature or pressure? No, which means?
Right, can't be solved.
For you to solve this question, you assumed standard temperature and pressure. Because if you didn't assume that, what's the answer, William?
Can't be solved.
It can't be solved. Okay? Because that conversion factor is unknown. Does that make sense? Okay. The reason I point that out is again because of how nuanced and tiny that conversion factor applies. It only applies in very specific circumstances. Okay? Last story, railing about STP. My wife is a process engineer, or when she had this problem, she's a process engineer working with big machinery, for lack of a better word, which she'd probably yell at me for using as a description of it, okay, where they flow gases over a heated sample so that they could make effectively solar cells. Okay, that was their process, was to make these things, solar cells or LEDs. They had a problem within the equipment. Couldn't figure out what was going on with it, so she broke it all down. These are gas flows. Let's figure out what the flow rate of the instrument is saying versus what we think it should be, and make sure they align. So she goes through to run calculations, way the hell off. Not even remotely close. She's like, this sounds like a big issue, but before she went out to talk to the manufacturer, she said, I want somebody else to crunch these numbers. So she brought it to me. I don't know why she did that, but she did. Okay? And I went through and looked at it and said, okay, well, these are gases, these are your relationships, this is how this will all crack out. Yeah, I got the exact same number she did. She still didn't trust me, which is fine. Okay? And she went and started talking to a variety of people about it. Okay? Standard temperature and pressure, like all these things should work. Standard temperature to an engineer, not 0 degrees Celsius. It was room temperature. Change the temperature, everything comes into alignment. Okay? Standard temperature is not standard. Depending on who you talk to, the number changes, which will drastically change all of your conversion processes. Okay? I want you to be aware of that so that when you go out, you recognize that when someone says, oh, it's obvious, it may not be obvious. Okay? Ask those questions.
It's more of a base than standard.
I'm not even sure how to respond to that.
For a group of people, but it is standard for the entire world. Like, it's standard if nobody is
Yeah. Yeah. I agree. Very frustrated by it. So, how many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid? Okay? This is now taking it to the next level. Okay? This is the exact same process we did with molarity, except now it is gases. Take another swing. Before we take another swing at it, what do we want for an answer? Liters of hydrogen. H or H2? Why H2? It just says hydrogen. When would it just be H? This would be one of the things I've said. That's okay. You forgot it. When it is explicitly stated as atoms of hydrogen. Is it explicitly stated as atoms of hydrogen? No. Then it is by definition diatomic. You must write it as H2. What are you given to start with? Grams of aluminum metal. Anybody see anything potentially challenging with that given information? It's not the right substance. It's not the right measurement. That could make things really challenging. Okay? It's running a reaction. This reaction is exothermic, which means it's going to release heat, which means it's going to get hot, which means...
Expand.
Yes, but that's not the important thing. It's not a standard temperature and pressure. Okay? Have we given you the answer on how to deal with not standard temperature and pressure? Nope, so don't worry about it. It's at standard temperature and pressure. We will make the assumption that that is true so that we can solve the question. Set it up. I want grams of aluminum converted into liters of hydrogen gas. We're going to go a little. You should have finished. For those of you wondering about time, gave you a good couple minute head start and then went through and showed all the work. For the record, all of the work. Right? Where everything is found, how to do the conversions, color coding the number sequence through this. Okay? Yes, I teach it, so I know it. But it also takes time to write it down. Okay? How many of you wrote down even half of the work? Okay? That's what you need to be working on. You need to be able to pick up that speed. Okay? For you to go through and do these questions, you have to have that speed. Time is a factor. Right? And where that time is really coming in is proving, do you know it or do you not? If you know it, you should be able to go through it that fast. Does that make sense? Right? You also know it takes time, which means skip it. Don't do it first. It takes time. During that same time that you're spending trying to solve that one question, you could have answered 2 or 3 other questions. Okay? If you've gotten the practice down where you can solve these fast, then yes, go ahead and do them first. Okay? If you aren't solving them fast, then move on. Okay? There's so much getting tested with a single question like this. Okay? Questions about what's up there? Okay. So, why are units? Okay, just keep hitting this home. How many moles in 9.8 grams? How many grams in 2.3 moles? Okay. In my method, it's dimensional analysis, where to find molar mass. For both. If you try to go through the standard method, you have to memorize an equation. You would then have to manipulate said equation for the other solve. And then you also have to memorize where to find molar mass. You're doing more work to memorize an equation. Why were you told to memorize equations in high school chemistry? Because it's very easy to test on. Okay? Did you memorize a fact? Cool, you knew that fact. Okay? And they can now say that you knew what was going on with that. I don't want you to memorize facts because you aren't going to use these facts. What I want you to memorize is a process behind how you do things so that when the question changes, you have a process to solve it without having to look up some special equation. Does that make sense? Okay? This one example just sets up and allows you to differentiate and see where that difference falls. Okay? When we look at gases, we've got this thing called pressure. It's the force or measure of the force of our air. We know there's a force of air because of this fancy little device. Okay? I take a container of liquid open to the atmosphere, and I take a tube, a glass tube that's open at one end, and I fill it with that same liquid. Okay? If I take that liquid or that tube and just turn it upside down, what's going to happen to all the liquid? It's going to fall out. Because of why? Gravity is going to pull the liquid out. But if I take that same tube and instead of dumping it just straight out, I very quickly put it underneath the liquid in here and then turn it upside down. Does all the liquid fall out? Is gravity not acting on it anymore? It is. So why is it not falling out? Okay. There's a pressure. What pressure? What gas pressure?
Atmospheric pressure on the outside.
There's atmospheric air. Come on, pen. Fine. Did that die? Is that what happened? There's air, pushing down on the liquid outside. For the liquid in the tube to go down, the liquid outside must do what? Go up. It can't go up because what is atmospheric pressure doing? Pushing down on it. Right? So we have evidence of this force. What makes this even more interesting is that if I leave this tube out and just let it kind of chill for a little while, I notice that the level of liquid in the tube will drop. Right? You might say, well, shouldn't it drop? Why should it drop? What happens if I take the tube out of the liquid? What's the liquid going to do? It's going to fall out. So why should it drop? Gravity. So seeing it fall down isn't a big deal. But what is interesting is what that liquid will sometimes do is go up. Why is the liquid going up? There's more pressure from the atmosphere pushing down on the liquid down there. That downward force on the liquid here forces the liquid up inside the tube. Okay? And what we're now monitoring is atmospheric pressure. What is the pressure of the air around us? And it does fluctuate. It fluctuates with temperature, weather patterns, and we can use the height in that tube to predict the weather. Okay? When it was first discovered, it was magic. And now it's science. I was going to go with meteorology, but science works too. Okay? It's just studying of weather patterns and being able to predict things. Okay? So that's kind of neat. Okay? There is something that's particularly of interest with that liquid. Okay? The liquid that is used is typically mercury. Okay? We don't use something like water. Why not?
You need a bigger device to measure level
If
pressure.
I left a beaker of water on the counter, what would happen if we came back to it next week? The water all disappears. And that's not because someone's drinking it. That's because the water is evaporating. It's turning into a gas. Okay? The ability for a liquid to turn into a gas, okay, has to do with something known as its vapor pressure. It's a physical property of that substance. All liquids and all substances have a vapor pressure. Substances have very small vapor pressures. Solids, for instance, typically have very low vapor pressures. What does that mean? A solid typically does not transition into the gas phase, which means what's its pressure? 0. There's no gas pushing outwards. So there's no pressure from the solid. Okay? Some liquids have a high vapor pressure, which means if I leave them out, they transition to the gas phase. Why would that be a problem with this device? If the water leaves, evaporates from here, is there any liquid keeping it inside? Nope. So what happens? This drops due to evaporation. So if we're monitoring atmospheric pressure, we need to have it exposed to the atmosphere so that it can be in contact with the atmosphere. But at the same time, it also needs to be a liquid that does not transition into the gas phase. That's mercury. Okay? Mercury has a very low vapor pressure. Other liquids have much higher vapor pressures. Water's one of them. Alcohols are others. Okay? So we could look at that pressure within a system. How could we monitor that? We could take a closed system here, look at the two tubes, the liquid's even. That means the pressure inside this half is the same as the pressure over there. Right? Because they're both the same height. Everybody agree? What happened over here? The left side is pushing harder on the liquid, causing the liquid to go down on the left and go up on the right. That difference is what we can call our vapor pressure. Okay? So if you think about your gas just pushing on the liquid, the more it pushes, the further from the liquid phase it gets. Okay? With that, we'll go ahead and take our break because I already talked a little bit too long. So we'll aim for 105.